Okay. Okay, note it down that in calcination is the process in which those who have not done, there are two processes. Actually, I need to make you because roasting and calcination is very important. So those who both have not done this one, so I'm going to start from here. It is very, very important. So Gianna, if you have done that one, it's okay, but you can rewrite it for more practice. Okay. So what is actually we have four types of fluid. One is sulfide ore, which is ending with zinc like sulfide ore, okay, like PBS, like ZNS, okay, Fe2S. So these are the sulfide ore, okay. And we have carbonate ores like CaCO3. This is having carbonate group like ZnCO3, okay. So it is if we convert this carbonate ore into their oxide form like calcium oxide and zinc oxide. And similarly, iron sulfide को भी if we are changing it from sulfide form to oxide form, FeO, FeO or PbO or ZnO, then it is easier to extract out metal from these two forms. It is easier to extract out metal from ZnO, PbO and FeO rather than ZnS, PbS and means. So we need to convert this sulfide ore into their oxide form and carbonate ore into their oxide form so that, okay, and carbonate ore into their oxide form. Why? Because their oxide forms are easily reducible. Understood? Their oxide forms are easily reducible. So it is very important for us that we must convert this. So to convert carbonate ore into oxide form, we do calcination. And calcination, C for calcination, it is done for carbonate ore. Here we heat the carbonate ore in the absence of air because there is already present oxygen here. So it will get converted into calcium oxide and carbon dioxide. And for sulfide ore, we do the roasting. So in roasting, what we does, we convert ZNS in the presence of oxygen. We heat in the presence of oxygen because it does not have already oxygen. So if we want to convert it into ZNO, we need an external oxygen. Na? बाहर से ऑक्सीजन की जरूरत पड़ेगी क्योंकि यहाँ पर तो है नहीं ऑक्सीजन. So and then sulfur dioxide. Okay. So we'll simply say that roasting is the process in which sulfide ores are converted into their oxide form, and calcination is the process in which carbonate ores are converted into their oxide. And why we are doing this? Because their oxide forms are easily reducible than their carbonate form. So start writing from here. From here, that why we are converting sulfide and carbonate ore into their oxide form. Why we are converting sulfide ore because sulfides forms are easily oxides forms are easily reducible than their carbonate forms and sulfide forms. Okay, oxide forms are jaldi se reducible. Note it down fast.
Done.
Okay. So note down this one, calcination and roasting. You done? Noted?
So what's volatile?
Volatile मतलब those substance that can be easily melted. Okay. With the some, like for example, we are heating it for at 900-degree temperature, and if we are heating it and it get melted, because at suppose there are some impurities that can melt at 300-degree temperature, 200-degree temperature, or 500-degree temperature. So these volatile impurities can be easily removed by melting, because that we are heating it at high temperature. So volatile impurities can be removed by this method. So the same advantages is for roasting also. So have you ever done? Noted? So why you join late? Please turn on your camera. Why you join late? Done.
Yes.
So what is roasting? It is the process of sulfide ore is heated strongly in the presence of oxygen or air to give metals, okay, metal oxides. And there should be the oxygen should be present in the present should oxygen should be present. You noted everyone?
Yes.
Those who have not done, please take the screenshot because should I move forward?
So can you show the advantages of roasting? It's not visible.
The same. It is same. Volatile impurities can be removed. Sulfide forms are more oxide forms are more easily reducible. The same. So let's move further. Now the next step is reduction. Reduction of ores. How can we reduce? Like for example, you have ores in the form of calcium carbonate. You convert it into calcium oxide by calcination. Okay, by calcination. Some ores, if it is in the ZNS form, when you convert it into you heat it by roasting, okay, you can convert it into Zn. But if these are with the oxide form, so reduction means removal of oxygen or removal of electronegative element. For example, you have NaCl. So how can we remove this Cl from it, and how can we get the pure Na? That is called reduction of force. So I'm just writing here. This is very important, and today's class is very important. So we must concentrate here, everyone. So I'm just writing the name of the ore like potassium, sodium, calcium, magnesium, aluminium. Then I'm writing chromium and manganese. And then after we have carbon. And after carbon, I have potassium, sodium, calcium, magnesium, chromium, manganese, carbon. Then we have zinc, iron, tin, lead. Okay. Then we have hydrogen, then silver, sorry, copper, then silver, copper, mercury, silver, gold, platinum. These metal exist in the native state. They are not found in the form of oxide. These the ore of these metals are generally found in the form of sulfide. So these metal can be reduced by simple roasting. By simple roasting. Let's study this one. Okay, like for example, you have copper, you have silver. Silver is in the form of Ag2S. Ag2S. When you heat this in the presence of oxygen, okay, roasting you are doing. So first it will get converted into HgO, HgO, HgS. This is not Hg2S, it is HgS. It will get and sulfur dioxide. The initial step you will get oxide form. So when you keep on heating, when you heat it, HgO, when you further heat it, it will give you finally Hg plus SO2 plus O2 plus O2. So, and similarly for the AGS, Ag2S, since silver sulfide is heated in the presence of oxygen, it will first give you Ag2O, then sulfur dioxide, and when you further heat it, Ag2O, when you keep on heating it, it will give you Ag plus O. Note it down fast. Done. And this is also the means this reaction. This reaction is also used for removing the black layer of. For example, if you have pure silver and if you kept it in the atmosphere, it again formed this layer, Ag2S. And this is the corrosion in silver. So corrosion of silver can also be removed by heating it in the presence of oxygen. Okay, so if silver sulfide is formed on the silver ornaments when it is kept in open air for long, then this again, this layer is formed Ag2S. Done.
Yes.
Okay, next. Move forward. Now again, this is very, very important. Reduction of copper. When you have Cu2S copper, when you heat it in the presence of oxygen, it will gives you roasting you are doing. It will give you Cu2O plus SO2. Okay. But let's suppose, don't write this statement. Stop writing first, Sumaya, and you Ibad. Suppose you went to the market and you buy only Cu2O and you want to heat it and you want to get Cu plus O2, it is not possible. Like in the previous sections, if you bought Ag2O from the market, you heat it, it will give you Ag plus O2. Or if you bring mercury oxide, you heat it, it will give you mercury plus oxygen gas. But if you bring copper oxide and you heat it, it will give you copper plus oxygen. अब यहाँ पर ये समझना है, you have to understand this thing, that this Cu2O, if you want to get copper and you bring only this, it required a reducing agent like carbon, like hydrogen, something we require. But since we are studying the economical process, and if we have Cu2S, then the crushed ore itself behave like a reducing agent. Means if you get this form, this Cu2O will further react with this Cu2S and will gives you again Cu plus SO2. And how we get that? Here the crushed ore is it's behaving like a reducing agent, because in both the steps we get sulfur dioxide, not the oxygen. Like here we get in the previous step we are getting the oxygen. Here we are getting the oxygen in the second step, but here in the both step we are getting sulfur dioxide. So this is the process when Cu2O and Cu2S are mixed together. We heat it, it gives you copper plus sulfur dioxide. Here the crushed ore itself behave as reducing agent. And the crushed ore itself behave as reducing agent. You understood? Yes or no?
Yes.
Note it down. The previous two have you noted?
Yes.
Done. Now
Yes.
moving to the next part here is that the other metals which are mid-reactive metals like zinc, oxygen, okay, zinc, iron, tin, lead. These metals are reduced with the help of carbon. I write in the carbon here. I'm writing carbon here just because to remind you, make that these from these metal carbon is more reactive. So if we have ZNS, so first we will convert it into ZNO. And when you heat it further, like for example, you have ZNS, you heat it by roasting. In the presence of oxygen, you heat it, it will get converted into ZNO plus sulfur dioxide. But if you further heat it, it will not get converted into Zn. You require a reducing agent here, like carbon, and it will get converted to Zn plus CO. So there you require a reducing agent. Here the crushed ore itself is not acting as a reducing agent. We require an external reducing agent, and like carbon. And why we are using carbon? Because carbon is cheaper metal and it is more reactive, easily available. Okay. So that's why, because we are here in the metallurgy, we are studying the economical process. Economical process means that require less expenditure and gives more profit. Okay. So we'll study that process. So here, if we are converting ZNS to Zn, first we will do roasting. And after roasting, we get oxide form. And then this oxide form is being converted into Zn when we heat it in the presence of carbon powder. Carbon powder with ZnO, powder of ZnO. When we heat it, it will give you Zn plus CO. Okay, zinc is more reactive than carbon. Sorry, carbon is more reactive than it can easily displace it. So this is very important for to understand that this is a type of displacement reaction. And reduction with carbon is called smelting. What we called it? Reduction with carbon is called smelting. Okay, so these metals are reduced, and reduction with carbon is called smelting. So note it down. Smelting, the reduction with carbon is called smelting. The mid-reactive metals, metal oxide cannot be reduced by simple roasting. They require a suitable reducing agent. And reduction by using carbon is called smelting.
So what's written after they require suitable?
Suitable reagent for reduction. Done?
Done.
Next. Now the reduction with, like you have seen this one, like this one's Fe2O3. When you heat it with carbon, it will give you Fe plus CO2. Zn plus, when heated with carbon, it will give Zn plus CO2. Lead, when you heated it with carbon, it's called. The next metals above aluminium is manganese and chromium. Chromium and manganese are more reactive than carbon, so it cannot be reduced with the help of carbon. They are reduced with above metal, that is aluminium. So, like if you have MnO2, you heat it with the presence of aluminium, then it will get converted into Al2O3 plus Mn in the liquid state. Okay. So it is very important that you need to understand that manganese and chromium are reduced with the help of aluminium. They are not reduced with the help of carbon. And a specialized name is given, like the previous one, when you reduction, when carbon is used as a reducing agent, we called it smelting. Similarly, reduction with aluminium is called aluminothermy. What we called it? Aluminothermy. Like MnO2 and Al. Stop writing first, listen to me. The reaction with MnO2 or chromium oxide, they are reduced with aluminium. This reaction is so exothermic that the heat liberated out during this reaction is so large that the metal obtained is in the liquid state. Okay. This metal, manganese and chromium that you are obtaining here, this will be in the liquid state. The heat produced is so large. Okay. That's why it is known as aluminothermy. Thermy means temperature. What we have, we take manganese oxide and aluminium powder mixture together, and then we use a simple a magnesium burning magnesium ribbon to it, and then it will, what it will does, it will initiate the reaction, and then the heat produced is so large that the metal obtained is in the liquid state. And we know that iron is a mid-reactive metal. It can be reduced with the help of carbon. Ibad, you are listening? So iron is the mid-reactive metals. Its oxide can be reduced with the help of carbon. Here you can see, because it is mid-reactive metal. But if we have iron powder and aluminium powder mixed together, and we reduce it with the help of aluminium, then again thermite reaction, this is a special name given to this reaction. Thermite reaction is done, in which we get the iron in the liquid state. Like here, this liquid iron is used for joining railway track and broken machineries. Like for example, you have iron track here, railway track here. You make it like this. I'm going to show you. And we have a powder of Al2O3, sorry, aluminium and Fe2O3. And we initiate this reaction by having burning magnesium ribbon. And then simply when this reaction start, the molten iron come in between this one. Okay, large amount of iron. Since you know that railway track joint is cannot be done by simple welding, you are welding the plant, because it requires large amount of iron. So we require large amount of iron that can fill the gap. 5 kilo, 10 kilo. We cannot do it like by welding. Okay, because welding can weld those when the sheets are connected. We have a gap and we need to fill that gap. So we require molten iron for that. And this molten iron can fill the gap when we have large amount of iron in the molten form. And the benefit of this thermite reaction is that the heat liberated out during this reaction is so large that the iron obtained is in the liquid state. So this can be used for welding purpose. Secondly, this can be done instantly on the railway track where we are doing. We cannot, if we have blast furnaces where we have melted iron, so you cannot have the blast furnaces for every 400, 500 meter. You cannot shift that furnaces to bring the molten iron to add there, because building a furnaces requires some stone. You cannot transport it everywhere. So you cannot melt the iron everywhere. Okay, large amount of heat, and this is very simple. Let me show you that how the thermite reactions take place. Let me show you. Here we have this. Okay. So this is the type that first we initially heat it, the railway track, and then we, okay, using this one so that we can heat the ends of both the track. Okay, so that when we heat it, so molten iron can easily fill it. Okay, then we put the can. Then we put the can here. This is the can. Okay, this is the can that is carrying the mixture of iron oxide and aluminum. And this reaction gets started when we put a burning magnesium ribbon to it, and this led the iron to obtain, even though the bottom of the container get melted, and the melted iron came in between it. So you can check it. The reaction is starting, and you can check that the molten iron is coming. This is the molten iron that is coming in the. So you can imagine that this reaction is so exothermic that the heat liberated out during the reaction led the iron to comes in the molten form. Okay, this is the molten iron that is coming in back. So this is used for joining the railway track and broken machineries. Understood?
Yes.
So, and the name of this specialized reaction is all our thermite means thermite reaction is a name is special given when iron oxide is treated with aluminium to give molten iron, which is used for joining railway track and broken machineries. This is the specialized name given to this thermite reactions. Okay, so it is very very important. So please note it down fast. The reduction with aluminium. Thermite reaction is used for joining railway track and broken machineries. Reduction with aluminium is done.
Done.
You also, everyone, so yeah, done. Next is reduction with, if I'm talking about that is the, now after the aluminium, we have these metals that are above aluminium, including aluminium. Okay. So for example, aluminium is in the form of aluminium oxide, calcium is in the form of calcium oxide, sodium is in the form of NaCl. So these are highly reactive metals and they generally form ionic bond, heavy metals, ionic bond. So the bond between is very strong and this cannot be broken. There is electrostatic bond. They have very high melting and boiling point and it will not be considered as economical process if we heat it because they melt at very high temperature like NaCl. So for this, what we do here is that uh, we have potassium, sodium, and this including aluminum. We did the reduction. If we have calcium oxide, like for initially we will have calcium carbonate, CaCO3. First we heat it in the absence of air. It will get converted into calcium oxide plus plus carbon dioxide. Then what we do here is that we heat the metal and convert it into the molten form. Calcium oxide is converted into molten form. Okay. And then, like for example, we heat it, we convert it into the molten form. And when we convert it into molten form, then we pass the electric current. So these metals that are at the top of the reactivity, including the aluminium and above the aluminium, they are reduced by electrolytic reduction. Electrolytic reduction method. There are two processes that we're going to study here. One is the electrolytic refining and electrolytic reduction. Refining is for the pure metal we did. Reduction is removal of oxygen or electronegative element. So electrolytic reduction is done for highly reactive metals. And electrolytic refining is done for low reactive metals or mid reactive metals. So for example, if I'm doing here, that is sodium chloride liquid. Okay, when we heat it, it will give you sodium in the molten form. And when we like you take this sodium chloride in the liquid state and you pass electricity to it, then it will give you Na solid plus chlorine gas. And how it does, let me explain you. Mark my point, we are using liquid. We are not taking aqueous. If it is aqueous NaCl, then it will give you chloralkali process. You remember formation of NaOH plus chlorine gas plus
Yes,
hydrogen
caustic
gas,
soda.
caustic soda. So this is the caustic soda will form. So we are not going to heat it aqueous. We heat it in the molten form. So when we take an electrolytic cell and we take inert electrodes, inert electrode means they do not participate in the reaction. And this is Na positive and Cl minus ion, Na positive and Cl minus ion, Na positive and Cl minus ion, and Cl minus ion. Then when we pass Na positive, you know that Na is positively charged, so it will goes to negatively charged electrode. This is cathode. So at cathode, what would happen? The two Na positive ion, or let me explain, let me write first the reaction with anode. So at anode, what was going to happen? The two Cl minus ion, let you explain me. Cl minus means chlorine with 8 electron in its outermost shell. Chlorine generally has 7 electron in its outermost shell, but when it is Cl minus, it means it has already borrowed 1 electron. So there are two Cl minus ion will lose their 1 electron from each and will form chlorine atom. Now these two chlorine atom will combine together and then form chlorine gas. So when they lose electron, they will become neutral and will become chlorine atom. Those two chloride ion will go and will form Cl2 plus 2 electrons. Understood? Got it?
Yes. Yeah.
And will form chlorine gas. Second is, and this is going to be done at anode. And at cathode, what would happen? The two Na positive ion, in order to balance two electrons, the two Na positive ion will take, because Na can hold one electron. Na positive, and what is the difference between Na ion and Na solid? Na, when lose one electron, it become Na positive and one electron. This is the ion. And when it goes back, it will again form Na solid. Means ions, when get one electron, it will form Na solid. This is the ionic form, that is in the aqueous. It is the solid form, atomic particle form. So similarly, when we have Na positive ion, two Na positive ion, when they receive two electrons, each one, then it will give you two Na solid. When we combine these two reactions, okay, so we'll get NaCl. When we pass electricity to it, it will give you Na solid plus chlorine gas. Got it? This is the way of electrolytic reduction of sodium chloride. Got it? Yes or no?
Yes, sir.
Yes.
So note it down this all.
Sir,
Okay.
out of when at cutoff, sodium is getting 2 electrons, right? So it will give out 2Na negative, it will become sodium minus.
No, because sodium is already having plus charge. If it is a neutral atom receiving the two electron without any charge, then it will get the minus charge. Like for example, Cl atom get one electron, it will convert it into Cl minus. But if Cl positive atom get one electron, it will become Cl only. Like sodium plus. If Na only Na is getting electron, one electron, then it will become Na negative. But if Na plus is getting, then it will cancel out this charge, Na plus, and will become Na square. Understood?
Yes.
Noted this one on. Okay, when you're done, you can leave. It's going to happen. Done, Jana?
Yes, sir.
Done? Okay, so that's all for today. Thanks for coming.
Thank you, sir.
Thank you, sir. Sir,
Yes.
actually, I want to help in biology.
Biology class, matlab?
Sir, for my midterm portions, I'm getting 3 chapters: life processes, control and coordination, and reproduction chapter. But
Okay.
we haven't really started the reproduction chapter yet, and my exams are really close, so I just want to get finished with the asexual part of reproduction. That's gonna come in my exams.
Asexual method of reproduction will need to come in your exams. Okay. मैं बात करता हूँ.
Okay. I actually requested a class, and they said they will look into it.
Okay, मैं करता हूँ. Most
Okay,
probably
thank
we're
you.
going to have a class. Okay.
Thank you, sir.
Hello, Anam, Zara, and Bharti. How are you? Please turn on your camera. And wait for 1 or 2 minutes so the other student also join. Okay. Hello, dear students. How are you? I'm audible to you. Everybody, please turn on the camera. Let us start studying. So, in the previous class, we were studying the dynamic theory postulates, and we were doing the questions. And we today we shall be going to learn the valency, okay, and how the chemical formula and the molecular mass is being calculated. We are going to discuss that. Okay, got it? So just a minute. First of all, before starting this one, let me explain you that what is valency. What is valency? What is valency? And valency is much better we're going to study in the next chapter, structure of atom, and we're going to let me explain you. There are some metals that exist in the not in the element. So,